Hi everyone. This is the first page of this chemistry lab, and some of the answers are written in and you can read them for yourself. I'm just going to point out a few that will help you understand the more difficult ones. The first I want to mention is hydrogen having no neutrons. That is how hydrogen exists when it is neutral. However, it can have neutrons. It can have one, two, or three. Here is the shell model of several of the elements that are important in our class. And you'll see group 1, top left, is hydrogen. It has one electron, one proton, one shell, and has no charge. However, it normally has no neutrons as well. To figure out the atomic weight or mass of an element is equal to the number of protons plus the number of neutrons. And if you look at the atomic weight of hydrogen, you'll see it is 1.0008. That means that the hydrogen elements that exist as neutrons are not that common. Most often, it has one neutron. That mass, the atomic mass, is an average of millions of hydrogen atoms weighed together. They consider the atomic mass with 0 neutrons, 1 neutron, 2 neutron, and 3 neutrons. And the average mass is going to be very close to 1 because the most common configuration of hydrogen is with no neutrons. However, the other elements, you will see 8 protons, 8 electrons, 8 neutrons. That again is an average, most common that you will see. If you look at the true periodic table, you will see that the atomic mass of hydrogen is not 8. It is not a whole number. It's 8 point something. And that again is the exact same thing. Oxygen can exist with 8 neutrons, 9 neutrons. It may have 7 neutrons. There are several different configurations. Every element can exist with different number of neutrons. These that exist with the less common configuration are called isotopes. Now, as we go down, sorry about that, 2, you will see that I drew it as well as I could. That is the shell model, and I think the next page shows carbon drawn much nicer. And if you look right here, this is carbon, group 14, period 2. Don't worry about what that means. You don't need to know it. Carbon has 6 protons, 6 neutrons. First shell can only hold 2 electrons, no matter what you do. Never more, always 2, except for hydrogen. Then if you have to start adding the electrons to the next shell. The max that any shell can hold is 8. Carbon, though, only has 4 in its outer shell, and that is the reason it is such a versatile element, because it can interact with up to 4 elements because it has 4 electrons. Now, for ions to exist, they lose or gain electrons. And hydrogen can lose that 1 electron very easily. And it's considered then a bare proton. I tried to draw it here. You can see this is hydrogen. It doesn't have a neutron in the nucleus. It's got a proton. And then the shell orbital has 1 electron. Now I tried to eliminate or erase that 1 electron and the shell because it no longer exists if it becomes ionized. And thus it is now a bare proton. That's all it is a proton. It doesn't have any shells around it. That is an ion, hydrogen with a positive charge. Back to this page, because what I wanted to show you was in C, 2C. You're going to go to potassium and then over to hydrogen. If you look, they both have a little plus sign. That means they've lost an electron. They have more protons, which are positively charged, than they have electrons. Hydrogen I just showed you. You're supposed to indicate the number of electrons in the outer shell. With hydrogen, there is no outer shell, so there are no electrons. Potassium, though, is a much larger element. So here's potassium. It's in the first column, 4th row. Its number is 19. So it has a lot more electrons and protons, and you can see the atomic mass there is 39.098. So it has isotopes. Here's potassium with the shell model. In the upper left, it is showing you 1 electron in the last shell, outer shell. It is not full. All of the inner shells are full. And that is how you build the shell model. The first shell around any atom can only have 2 electrons. The second shell here has 8. The third shell has 8. So that's 16 plus 2, which is 17. It has to have 1 more. So the last shell is going to have that 1 electron. Instead of 17, I mean 18. I'm sorry. Okay. Sorry about that. I can't fix this because I don't have the time. So you'll have to ignore my skips back and forth. The picture to the right is showing you an ionized potassium. The little plus sign indicates it's lost the outer shell. Thus, in that, you can see the last outer shell has 8. Go back to that first question, C, and potassium. It wants to know the number of electrons in the outer shell. Its number is 8. And it's this picture. Okay, this is the second page. And it's CaCl2, calcium chloride. You can see the direction the electrons went. Calcium is positively charged because that means it lost its outer shell. It lost 2 electrons, and it gave them to chlorine. It gave 1 to one chlorine, 1 to the other. Because it lost electrons does not mean it had to give it to this one element. It can give it any way it wants. Thus now chlorine has a negative charge because it got an extra electron to fill its outer shell, which only had 7 electrons in it. Thus now it has 8. Remember, they have to be full. So an electron shell wants 8. It is happy with 8. Hydrogen is happy with 2 in its outer shell because that's all that would ever have. So whenever you're looking at these outer shells, we're really looking at energy levels. And electrons are in constant motion. But they are looking to be stable. And when CaCl2 ionically bonds together, it gave up its electrons. So an ionic bond only forms when it gives up the electrons. A covalent bond, on the other hand, doesn't give up electrons, it shares electrons. And that's what it's doing in methane. Each of these lines indicate a covalent bond. So these are each single covalent bonds. Ammonia, NH3, single covalent bonds. CO2, carbon has to have 4 electrons used. It's got 4 electrons in its outer shell. It wants 8. So in this situation, it is going to share 2 with oxygen and share 2 with the other oxygen. So oxygen thinks it has 8 in its outer shell, and carbon thinks it has 8 in its outer shell. I'm sorry, here, the last picture is oxygen. It is showing O with a double covalent bond with O. Each oxygen has 6 in its outer shell. It needs 2 more to be happy with 8 in its outer shell. In this situation, oxygen is covalently bonded with oxygen in a double covalent bond. Hi, I've added 2 slides, so this is an addition. Hopefully you'll see it. I just wanted to go over covalent bonds. Covalents are different than ionic. Covalent means they are sharing the electrons. There are many subsets of covalent, as you're going to see. There's a single, which means they're sharing 2 electrons, 1 each, or a pair. A double covalent means they're sharing 2 electrons each, or 4. A triple covalent, which you don't see that often, but that means it's sharing 3 each. Now, these are demonstrated differently. As you look here, you'll see methane, HC4. This is what you were doing in the lab, which was a model you were to build. Now, the building is made up of 1 carbon, 4 hydrogens. And it can be demonstrated many different ways, as you can see. The first drawing over here shows individual, and it only shows the outer shell. And what's going to happen is the carbon and the hydrogen are going to unite, as shown in the next picture, and they are sharing the 2 electrons. And they both think that they have that extra electron around themselves. Thus, hydrogen's very happy because it has 2 in its outer shell. Carbon still needs 3 more hydrogens in order to get 8 electrons in its outer shell. If you count all the little blue dots, you will see that there are 8 electrons now, and carbon is getting 4 from hydrogen, 1 from each hydrogen. And the line indicates a single covalent bond. It means 1 pair of electrons. Now, these bonds can also be polarized. And that happens with water. And please listen to the lecture I did about water, as the polar covalent bonds are not the hydrogen bonds. The hydrogen bonds are different. Okay, back to this. Up at the fluorine, it also is going to share a single pair of electrons. It becomes a different element. It's called difluorine molecule, and its di usually means 2. 2 fluorines are sharing an electron pair. It's a single covalent bond, and it would be demonstrated with F line F. Just like the methane down here, single lines. Okay, now I'm going to show you a double covalent bond with oxygen. That again is another molecule you were building in lab. Oxygen needs 2 electrons to have a complete outer shell. It has 6 in its outer shell and 2 in the inner shell, which is all the inner shell can ever have. So these 2 oxygens are going to join together in a double covalent bond, and they are going to now be sharing 4 electrons, 2 pairs, which means a pair of electrons are 2 from 1 oxygen, and 2, or a pair, from the other oxygen, just like a pair of socks. A pair means 2. The picture on the bottom is another demo of the same thing. With the number 2 and 6, they are indicating 2 in the first shell, 6 in the outer shell. This one is showing you the electrons just as the top picture did, it's just colored. And then when O2, and here you see O2 is a molecule, that means there's 2 oxygen bonded together in a covalent bond. It's not a polar covalent bond. It is a double covalent bond. You can have a triple covalent bond. Nitrogen can do that. We didn't do that in lab. Our model kit would not allow for that. The springs were used for a double covalent bond. Now, water is unique, H2O. It looks like Mickey Mouse ears. Okay, here we have water, H2O. One oxygen, two hydrogens. Now, I want you to see that the H in the top, O in the bottom here, it is sharing one pair of electrons. That is a single covalent bond. This hydrogen with oxygen is sharing two electrons. Single covalent bond. But we have created a polar molecule. Thus, these covalent bonds are polarized. And what you see here is a negative. What that means is oxygen is bigger. You can see the size. And look at all the blue electrons along the outer edge. Electrons are negative. If the electrons are negative and you see a lot of them on this side, that means they're spending a lot of time over here. Thus, the oxygen end is actually slightly negatively charged. However, you go to the hydrogen, there are no electrons. There's nothing. There is just a proton. That proton is positively charged. So the number of electrons at the hydrogen end is much less. Thus, they are positively charged very slightly, but enough to make it a polar covalent bond. It has polarized the water molecule. It looks like Mickey Mouse. Turn it upside down and you can, or sideways, and you can see that the hydrogen looks like the ears, the oxygen looks like the face. Okay, the bottom picture, little different model of hydrogen, H2O, but the red is oxygen, the blue is hydrogen down here. And then you see those little black lines connecting. They're not connecting, they're not sharing electrons. But there is a negative end, the oxygen, attracted to the hydrogen end, which is positive. Thus, the hydrogen and the oxygen are attracted to each other. That attraction is a bond, very light bond. It's not strong. No electrons were given up. No electrons are being shared. It is only due to the relationship of the bonds that made the water. Thus, you see hydrogen bonds, and this is how water forms. It is what causes the properties of water that you see. If you look at a top of the car after you waxed it and it rained, you see droplets, but they're in this circular shape. That is because of the negative ends being attracted to the positive and being pulled in towards the water, not the air. This property is also why water will go up a stem against gravity to the tree top or a plant top. That is how the water gets up there. It is because of this negative positive attraction. I hope this helps you understand. I did go over this in lecture as well. So go to your normal lecture. Also read in your textbook and your lab book. All of this is covered many times. Have a good one.